It all begins from a single origin, a unique point in space and time. This is the spark of innovation that fuels your most amazing breakthroughs. It's a passion for discovery that unveiled the genesis of all that exists in the universe. Today, the power of AI helps computers achieve superhuman capabilities in image recognition, and lets scientists save our most precious resources by analyzing in 1 month what used to take 10 years.
是谁发明了机械计算机？
Everyday devices translate even the most complex languages from voice into text, and images into words.
Xavier is now present.
Helping the visually impaired recognize an old friend, or letting a blind woman read to her child for the first time. Autonomous vehicles give us the freedom to reimagine our city streets and travel where there are no streets at all to help the lost find their way home. We see robots teach themselves to perform simple tasks. We even watch in awe as they take their first steps. And today, a 2,500-year-old game meets its match as a computer competes with one of the greatest human champions of all time and wins. This is the collective imagination, fueled by forward-looking technologies and the beginning of your most amazing discoveries yet to come.
Okay, so I hope that's woken everyone up. Certainly to the world of AI and GPU computing. But just to start off with, so my name is Jack Watts, as explained earlier. I'm the Deep Learning Startup Business Manager for Northern Europe. So that doesn't really, in the American sense of Northern Europe, actually only really includes UK, Iceland, and the Nordic countries. So no actual part of Northern Europe, which is a bit strange, but I digress. So effectively, Nvidia is a GPU computing company, so the graphics processing unit. So we've primarily put beautiful graphics on computer screens. So whether that's to play Call of Duty at the highest frame rate that you can, so that you can beat all of your buddies over the internet, or whether that's in virtual reality with our computing platform for that. To again, either collaborate in different space with your colleagues in an architecture sense, or to design movies and what have you. Speaking of movies, we're used in 9 out of 10 movies today for the computer-generated images that you'll see on the screen there. But that's our traditional, that's our bread and butter business, and it's a multi-billion-dollar business today. There's over 100 million gamers on the planet that use NVIDIA's GeForce technology. You'll see us now in lots of other different types of technologies as well. So in self-driving cars, we are in the latest autopilot with Tesla. If you're lucky enough to own one, you can drive down a motorway hands-free. It will remind you every now and again to, of course, put your hand on the steering wheel just to make sure there's still someone actually sat there paying attention. We're also into in MRI machines, in other medical applications, and then also into other supercomputing applications as well. So helping to simulate whether that's molecular sciences, bioinformatics, and even cancer and stem cell research. High performance computing is also becoming a more and more important aspect of NVIDIA's daily life. So Nvidia really is the computing driver and really is the use case for the most demanding users. So as I mentioned, for high-performance computing, computing the human imagination in terms of computer graphics for games, for movies and so on, and now also into this new paradigm of artificial intelligence, helping, as you saw, the robot from the video earlier, it's a self-learning robot. So you present it with something, and based on a very remedial training engine, it's able to then pick up objects and then actually decide, where that goes, whether that's a square peg to go into a square hole, a round peg to go into a round hole, and so on. And then also you saw the AlphaGo competition. So Lee Sedol was the reigning champion of the world of playing AlphaGo, which is a game which has 100 million more complex moves than the game of chess, has now been beaten by artificial intelligence, by Google DeepMind, a British company, I might add, actually. So deep learning is really the new computing model. So effectively, you take a data set. So for example, in images and classifying images, you take hundreds of thousands or even just thousands of images that have been pre-classified. So this is a cat, this is a dog, and so on. Then you pass that through a learning algorithm, which is a neural network construed of numerous layers and filters, which will recognize, to begin with, it will start to recognize the outer layers, for example, shapes and lines. Then it will start to understand depth and then build features from that. So whether that's a nose, an eye, an ear, and so on. Is that a nose of a dog or a nose of a cat or a nose of a human? And then when you've trained that neural network, you can then present it a new image, an untested image, and it will tell you that's a baby eating what was that? A bit of birthday cake, I think. So that's where you start from something quite simple in terms of thousands of images. You pass it through this algorithm, and then you can present it with new images afterwards. So it really started to happen, certainly for Nvidia, should I say, in around 2012, when it was called the ImageNet Computing Challenge, which is, again, several thousand images trained on what was at the time CPU-based infrastructure, so the general processors that are used in computers and servers today. And then what effectively happened is that people started porting that code over to GPUs, and they used a framework called Caffe, not where you get a general coffee or what have you, but it's a framework which effectively is like a toolbox that people use to then train a neural network accelerated by GPUs. So it used to take weeks to train these neural networks on CPUs because they're effectively serial-based processors. They take one instruction and they compute it one after the other, whereas GPUs have thousands of cores. So you can present thousands of instructions and they'll do them all in one flop. So when it comes to producing pixels on a screen or processing images, GPUs are really good at that. So you get what's called the accuracy curve. So the accuracy is obviously how accurate that computer is at determining what's inside that image. So hand-coded computer vision versus deep learning, and you can see the accuracy is well actually beyond 96% now. In fact, it's in the order of 98 to 99%. Some of the applications that I'm sure you're all familiar with, Facebook, Shazam, Skype, Twitter, and so on, are all powered by artificial intelligence and GPUs today. So whatever you touch nowadays, certainly if you ever use Google or any of the applications up there, you're touching an element of artificial intelligence. That is surprising to some people. So AI really is the next trillion-dollar opportunity. This is a report from Tractica where effectively they sort of profile the market and to understand what industries will actually be able to take advantage of artificial intelligence. And the short answer is that every industry can take advantage of artificial intelligence, whether it's designing a new car, understanding how to navigate a car down a road, or whether it's to effectively to tell you what's inside a picture that you've taken and posted on Facebook. One of the scary examples is, for example, when you're standing in a bar and someone else takes a picture of you, not intentionally, they're taking pictures of their friends or a selfie or what have you. They then post that to Facebook or Instagram or what have you. You will get an alert on your phone, you're completely unconnected, and it will say, your face has been recognized and taken in this photo, do you want to obscure your face? That could be an interesting application that's not too far around the corner. Fast forward maybe five or 10 years, you'll be taking a selfie and then it might have a mole on your face, and Facebook will say, you might want to get that mole checked out. So where can you do deep learning? Really, you can do it everywhere, and especially with Nvidia GPUs. So we start off with researchers and development type scenarios inside the PC, inside a laptop, or in the cloud. And of course, we have our own appliance, which we've built called the DGX1, which I'll cover in a moment. But really, we can do it anywhere from that kind of type of device where you just sort of trying out your application, trying out these training models, and then you can really start to then deploy it in production, in the cloud, in your own dedicated infrastructure, or with a supercomputing appliance. So last year we announced this appliance called the Nvidia DGX1. It's a 170 teraflop appliance. Teraflops is a computing, effectively, it's a speed, if you like. So you take a normal iPhone, for example, that will do so many gigaflops. This is in the order of 10 to the power of 14. So we're talking huge amount of computation performance. This is where you deploy your applications later on. And we're not just a hardware company, we are in fact very much into the software stack as well. So when it comes to supporting these frameworks, I mentioned Caffe earlier, there's Torch, Theano, TensorFlow from Google and so on. We effectively accelerate those specifically on the DGX1, and we deliver those in a containerized form. So for researchers, for data scientists, they can get going and not becoming their own sort of system administrators, if you like. They can just focus on what they're actually being paid for. We then, of course, take care of the entire stack, from the hardware to the middleware, and then, of course, the software on top. And we also include our Digits platform, which is a way of actually visualizing how the neural networks are being trained. And access to NVIDIA and access to deep learning expertise really is at every step. So that's our own engineers, our own solution architects and developer technicians. We actually have our own conferences called the GPU Technology Conference. We initially only had those in the US. We now have those in several locations. The one in Europe will be in October, later this year, in Munich. And it's when researchers, where scientists and commercial people come along to understand, what's the new applications coming out in artificial intelligence, and really where can I go from there. And then we also have on-demand Deep Learning Institute courses, which I'll talk about in a moment. So really, deep learning is sweeping across all industries. So from cancer detection to obviously the applications that I mentioned earlier, captioning video. So when it comes to live broadcast streams by news outlets and so on, they can understand what's inside that video and then effectively point you towards advertising or point you towards other videos that you might be interested in, whether it's facial recognition and cybersecurity and various other applications as well. Obviously, we talked about deep learning in the car as well. So I just wanted to talk about a couple of use cases. These are actual startup companies that I work with that have taken their own grasp of what they actually do in their day-to-day lives, and then actually applied that to deep learning. So AI Build is a company that has actually been founded by architects. So not only architects that have worked for the well-renowned architects like Zaha Hadid or Foster and Partners, have designed buildings like the Apple's new donut or spaceship, whatever you want to call it, that's going to be over in Santa Clara, I think, roughly around there, Northern California anyway. So effectively, they were sort of struggling with the notion that traditional construction today is brick by brick. So what if you can actually build that into having robotics help and assist doing that? So can I design a robot that can then use industrial scale 3D printing to build a wall? So as you can see, what they've done is they've taken a industrial sized robot. So this robot will take sort of 3 meters tall by 1 meter squared wide. It can print up to 4 meters wide as well. Has an extremely high precision algorithm to it. But again, when you're talking about extruding materials from a needle that's a hot material, it then cools down, and obviously, you might be in different types of environments and so on. But the real issue is what happens if that material there isn't enough material to make that structure stable. So they use not only Microsoft Kinect cameras, but additional cameras connected to one of our mobile processors, which you can see in this little glorified machine, if you like, on the right-hand side that looks a bit like Terminator's eye. T1000, if you like, and effectively they're able to see how the material is being extruded, how it's drying, and whether they need to apply more material to it. So at the moment, it takes about a day to build a single panel of wall, but you can imagine in the future that these things will get faster with more and more learning. So they really are pioneering the large-scale 3D printing, and they plan to build a house later this year. So this is a company that I've worked with for a couple of years now. This is Intelligent Voice. So these guys take telephone calls and live streamed audio, if you like, and then convert that into text. You might think that's actually quite easy to do. It's actually really hard. We all speak differently. I speak very funny, I'm sure, to the way you guys speak, of course. But I'm speaking, obviously, my native tongue. When you're actually speaking another language, obviously, that's again very different and a very different dialect that you're speaking there. These guys are also doing it via phone calls as well. So when you speak to Siri or Cortana or Google Now, you're actually sending a fairly clean sentence, if you like, or instruction up to the cloud, and it's getting that worked on. When we talk about phone calls, these are heavily compressed phone calls that are then potentially even stored on another machine, compressed further, and so on. So you actually get like a really unclean and a very trimmed sonograph that's coming out of that. So what these guys do is they take that and then they put it through their algorithm, and then they not only initially detect what language is being spoken and then what dialect, that they then pass that through their algorithm and get incredibly accurate speech transcribed from the end of that. What they're able to do with that data afterwards is actually give you a histogram type view of that conversation, what topics were discussed, what was the emotion behind those topics, and so on. This comes in particular handy for, we're talking about scandals or potential issues within a banking or finance sector, where they're talking about insider trading and various other things, and they want to be able to understand what's coming out of the back of that. So the issue around that is, where do I get this data? How do I view that data? Because we could be talking about hundreds of phone calls over hundreds of hours. So that's where these guys really come in. And they also then combine that with text messages and emails, instant messages, and so on. So they're a really interesting company and someone that we've been working with for a while. Again, they couldn't do it without GPU technology. It would just be impossible to do on CPU-based technology. So another company is actually in the drug discovery market. So it can take anything between 10 and 14 years to produce a new drug, whether that's to cure the common cold or whether that's to help with sinus infections or whatever it is. And you can imagine that costs billions of dollars to go from compiling the compounds to then go to actually trialing that with humans, and then obviously getting that into production. So what these guys do is they actually trawl through hundreds of thousands, if not millions, of articles, new updates that are published to PubMedical, which are actually, there's one new update every 30 seconds. They then also take patent information from the conglomerates that are the pharmaceutical companies, and they effectively look for the chemical compounds that react to different types of proteins that are in the human body. What they then take from that information is, could Nurofen or an ibuprofen type drug help with Alzheimer's or help with ALS or what have you? So they actually put this into practice, and they've been working with this and actually using what's called their Judgment Augmented Correlation System, or JAX for short, definitely not named after me. And they effectively put that through, and then they pass that information to their data scientists. So this information, we're talking again, hundreds of millions, if not thousands and thousands of articles, of patents, of updates to PubMed. That's beyond human comprehension, right? So if they can provide a targeted view of that information to their scientists, they can then obviously work to producing these drugs. And they've actually already put this into practice, and they have actually discovered a drug that's going to go into trial late next year, and that will be for ALS, which is something that touches, if not your first, but your second or third degree connections. Another company called Imagery, so this is large-scale image classification for mobile and internet-based devices. They're, again, an Israeli company, but these guys, effectively, they're able to train using a wider network of images. So they've used anything from working on sort of focused type images, so for example flowers, or for dresses or suits, to now they're actually working on concealment of weapons, for example, for a CCTV company. So these guys have started with something relatively simple and they've taken it to the next level. So when we're talking about cats and dogs earlier and human faces, these guys really take it to the next level and look for concealed information from what's actually inside an image. So what do Nvidia really want from this show and from talking to some various people is Iceland is not only one of an extremely innovative hub when it comes to startup and software companies, but also we work very closely with our startup companies. So we have what's called the Nvidia Inception program. So it gives you access to deep learning expertise. It's also all about GPUs, so we give access to proprietary hardware, early access to hardware and software. We also provide training, so we have an online coursing available called Quick Labs, which trains on all the major frameworks in a on-demand type classroom environment, and then we also take that into the universities and into organizations as well. We also give the startup company marketing exposure. So I've worked with many companies over the last couple of years, and we've provided them with access to success stories and also to joint PR opportunities. In addition to that, we also have our GPU Ventures program. So our GPU Ventures program is something that we actually have our own venture capitalist arm in Nvidia that we actually invest in companies. So we made some strategic investments last year, and we effectively work alongside venture capitalist firms and then help, again, boost especially if it's an interesting and a really cool type of technology or something that's going to affect us socially or responsibly, then we will potentially invest in that company. So the Deep Learning Institute, as I mentioned, is on these online courses or in-person courses. So these really are workshops that help you get started with deep learning. So you do need to have a basic understanding of calculus, but you don't necessarily need to be, really a pioneer in your field, if you like. The Introduction 101 course to deep learning I've done online, and I managed to pass it, so I can't be too bad. I did have a little bit of help, I won't lie. But certainly if you have a look at nvidia.co.uk/DLI, you'll be able to understand a bit more information from that. So additional resources, so we've got technical blogs, partner courses that we deliver. We then also work with organizations that were wanting to get started with deep learning. Will either come in and do a dedicated course, or they can obviously go online and do the self-paced labs. So that's everything from me. I really hope you enjoyed the presentation, and I won't hold you off from any more rubbish from myself. I'd like to obviously thank you again and enjoy the beers this evening. Thank you.
Þá komið að lokum hérna í dag. Ef það eru spurningar fyrir tjá, hljótaðu einhverjar. Við höfum tíma fyrir svona 2-3 spurningar. Gjörðu svo. Á ensku, já. Ég skal þýða annars.
Sure. So I mentioned earlier about it taking between 10 and 14 years for a drug to be developed and go into production. The question was, how long did the AI take to actually do that? So obviously this is a drug that's being proposed to go into production after clinical trials. This took 16 days. So 10 to 14 years, billions upon billions of dollars, down to 16 days. All right, and that's obviously a proposal of a chemical compound that they can then take, simulate, and then put into production.
There's another question over there.
Question answered. Yes?
Has Nvidia had anything to do with general artificial intelligence and consciousness?
So the question about consciousness, we're far away from that, I believe. The way that we're working today, and certainly the way that startup companies, even the likes of Google, Facebook, and so on, that are using AI today, it's in a very verticalized fashion. So they're doing image classification, they're translating speech to text, they're presenting a new image of an MRI scan, and then saying, okay, that's something that we need to look at further. We need to take a biopsy of that, or it's malignant, or it's a passive cell that we can pass off. It's fine. In terms of horizontal plays, I see very little work being done to do that. So, we're talking about lots of different applications that will work in their own fashion. When it comes to them all working together, I think we don't really have the computational power today to be able to realize that. Quantum computing's really starting to take shape now, but still, you need billions upon billions of dollars to invest to actually buy a quantum computer. So really, that's going to take a while. So for those of you sci-fi fans, when we would look at the likes of Ex Machina, or Her, or various other movies, I think we're 10 to 15, maybe even 20 years away from that. But obviously, you've got organizations like OpenAI that are working as kind of like the AI police, if you like. So how do you know if an AI is going to go bad?
Yep.
You've shown us a solution with general purpose GPUs. Have you also tried using or looking into using application-specific PASICs or
Certainly. So I mentioned earlier general purpose GPUs computing. So that's our bread and butter when it comes to high performance computing. Have we looked at integrated circuits or dedicated for applications? Nvidia personally, no, we haven't. We have different form factors of GPUs. So those that sit inside PCs, inside laptops, or inside mobile devices, and that are going into robotics. So little credit card sized GPUs, which are actually system on chips. So combined with ARM chips, ARM CPUs. So we haven't looked at a focused market for that, because we don't really see an application for that that's going to be consumed in the hundreds of thousands, if not millions, of chips at a time. There are some companies that are producing their own chips to do one specific thing, but again, I mentioned earlier, general purpose GPU, right? So you can take an application from one GPU, deploy it on another GPU, you'll just get a different performance profile. When it comes to it's being coded in our language or using a framework, and then you want to run it on the next generation GPU, it will run. There's no need to recode. With the likes of FPGAs and integrated circuits, every time there's a new design, there's a new way of coding that, and there's a new application you need to put on top of that. So it costs a lot more money to work in that manner. I hope that answers your question.
All right.
Okay.
Thank you, Jack.
All right. Thanks, everyone.
So,
Cheers.
Takk kærlega fyrir sessunni í dag. Takk Jack.